Welcome to lesson 3, example number 7. And in this example, they are asking us to find the required bearing area. And they've given us that the reaction is 8,000 pounds, and that what we have is an 8 by 10 dense number 1 Douglas fir beam. So they're asking us what is required bearing area. So if we have the fir beam, the Douglas fir beam coming in like so, how big does this post need to be? Sorry, it's not the best sketch in the world, but what is this bearing area? So we know at first it says 8 by 10. All right, that sounds good. But let's think about what equations are we looking for here? And so, for instance, if we take a look back real quick, let's say it's a simple beam, and you have this is 8,000 pounds. All right, so that's our equation, or not our equation, our reaction. Excuse me, and what it looks like it has 8,000 pounds coming down right there. So that's a reaction, of course, and everything has an equal and opposite reaction. So it's actually putting 8,000 pounds going down. You have to resist it 8,000 pounds going up, and that's what the reaction looks like. Kind of explain what a reaction is. Anyways, we have to transfer this stress right here, the 8,000 pounds, to this column, this timber column, let's call it. So we have to figure out what is that bearing area. What can this Douglas fir handle? So let's think about it. It's an axial load coming down, and we have to figure out actually what is the allowable stress. And it's kind of hard to think about. I'm going to go ahead and draw in the grain. The grain is like this. Sorry, this is not the best. And then this grain is going like that, let's say. Let's say be what you want, because wood is very strong and in the parallel. For instance, if you have a beam, you don't want to, and obviously you're not going to get a huge beam that the grains are going to be like this. So hopefully that makes sense. That wood is really good when you either compress it or you put it in tension this way, parallel with the grain, and it's not as good perpendicular to the grain. So I like to look at this problem as a simple stress and compression equals P over A. And we've done that before. So you want to figure out what area can handle that stress, or that P. And the P is 8,000 pounds. So we know P is 8,000 pounds. We can figure out area, and then we can figure out what we're going to get. But we don't know the area, the bearing area. What we know is that it's 8 by 10. So we know that the cross section looks like this. It's 8 by 10, so it's almost a square, but not really. This is 8 by 10. And I would look up these are nominal values, and let's look up the actual values. Actually, before we do that, let's just go ahead and solve the problem. What we need to do, if we know we have what? We know what wood we're using, so we know what this is going to be. We also know what this is going to be. We just solve for A. To the table on page 44, and let me go back real quick. Alt Z, no, Control Z. All right. We want to figure out what we get here. FC perpendicular, and we go over, and it is 730 psi, and that's our allowable. So we know how much we can get. This is our max. So we have to figure out what our min A is, and we had looked at that the same video. If you're looking for your max, then you have to figure out your min over here, since it's on the bottom and they're inverse related. And if you go higher on A, if A gets bigger, obviously the compressive stress is going to get lower. The more A you get, the lower this number is going to be. And I hope that makes sense to you. If not, just throw in some numbers. Say, hey, I'm going to make A equal 100, I'm going to make equal 150, A equal 200, and so on and so forth. So we have FC in the perpendicular direction. Remember, it's perpendicular because we're talking about this right here, and it's going to be crushing like that. So let's think about compression like so, as opposed to crushing in that direction, which is going to be the strong direction, or the parallel to the grain. Alright, so we have FC perpendicular equals 730. We can go ahead and say that's equal to P over A, which P is 8,000 pounds over A, which will be in inches squared. So let's just figure out what this is going to be in a perfect world. If you don't need to figure out, if you're not told you have an 8 by 10, and it looks like in the example on the study guide they don't go ahead and figure out what I would figure out. But anyways, let's do this. In a perfect world, this is the area, and this is exactly what they're asking for. So let's just give them what they asked for initially. I gotta reach my calculator. All right, 8,000 divided by 730. That's 10.96. Let's check that out. Yeah, that's what they got as well. 10.9 inches squared. That's just 8,000 divided by 730. A goes to that side. 730 goes to underneath. Hopefully that makes sense to you. And then, so this is the minimum. Let's call that minimum area that we need. And what I would challenge you to say, hey, well, go up here. If you're actually going to do this, you have to figure out, well, what do I need to put bearing on? In a real world situation, 10.96, somebody's going to look at that and be like, oh, well, thanks, that's useless. Let's turn that in a real world situation. I'll color some different, change the color. We know we have an 8 by 10. And let's look at the nominal compared to the actual dimensions. And the actual is 7.5 and 9.5 inches, of course. Alright, so this was our theoretical answer is right there. And usually that's going to get you just fine, but let's go ahead and turn it into a real world situation like I just said. And 7.5 inches is actual. So if you're thinking about it, you're already going to have 7.5 inches deep. Doesn't matter how tall it is, we do not care at this section. So you're going to have 7.5 inches deep. So you have to say, okay, well, if I divide this by 7.5, then that'll tell me what is this minimum length. Let's call, this is going to be width times length. Let's call it min L. So if we take, and this is W right here, let's call it W, width times length. This will be height, but we don't use it in this equation. So A equals W times L is what we're saying. Hopefully that makes sense. W equals, A equals W, means this dimension, times the length of the bearing area. So let's go ahead and fill that in. And we have what, 10.96 inches squared equals W, which we know is 7.5, since they've told us that we have an 8 by 10. And then we need to figure out L. Well, let's go ahead and solve for L now. And that's a pretty easy equation. 10.96 divided by 7.5 gets us 1.46 inches. Alright, so in real life, this is what you need this dimension to be. This beam, or this column or post underneath needs to be at least 8 inches across, or nominally 8, with actual 7.5, times, at least it needs to be 1.46, which that doesn't seem like an issue. So if you want it to be an 8 by something, it needs to be an 8 by 8 by 2 at the least, which that's probably not going to happen. So you say, well, maybe real life, what would work here? An 8 by something? Well, you're probably not going to do that. Maybe you want to make it a little bit smaller. Maybe just an 8 by 8. You could do that. That would make sense. Or you could go in and say, well, what's a 6 by 6? Let's pull this up. Actually, what's like a 6 by 6? The area of a 6 by 6 is 5.5 times 5.5 equals what? I can't do that in my head. 30.25. That's plenty. let's say 4x4 post. In reality, you're probably not going to have any issues with this. A 4x4, 3.5 times 3.5, looks like they're ½ inch off each. 12.25. So the area equals 12.25 inches squared of a, what I say, 4x4. So that's probably the minimum I'd specify. But then again, you can go in and just, if you're designing, let's say, you say, oh, well, a 4x4 minimum or area equivalent or greater. And that would give you a little bit of factor safety. Obviously, they're not going to put it directly underneath. Maybe they'll overhang it a little bit. And it's up to the designer. You know, what if they put it over here a little bit as opposed to it. And it's kind of up to the designer how you want to do that. And it's more probably dependent on your codes that you're looking at. But that's a little bit more of a real world example. 10.96, you're not going to get a piece of lumber that's exactly 10.96 area to fill that timber post underneath. You know, which in real life, you know what I do? I go 8x8. Call it good. Alright, then you get plenty and plenty of area to give. Alright, thanks, and we'll see you on the next video.